It's a rich girl and it's gone too far. Da da ba da 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 da. On old man money, you can rely on old man. Ba, 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 ba. In this video, we are going to be, oh my goodness. In this video, we're going to talk about the design of an observer in state space. So let's put the title up here. It's Observer Design Using Pole Placement. All right, just like we have done full state feedback control design, we can also place the poles of an observer. So here's the deal. We need to estimate the state of the plant, the state of the system, the states, X, based on the available information I have. So we need an estimate of the states, X. This happens when we don't know all the states, when they can't be directly measured. So let's suppose I'm given a standard state space system, linear time invariant causal dynamic system. AX or X dot is AX plus BU, and Y is equal to CX is my output equation. Then let's define a new variable, which I'll call X hat, and that's going to be my estimated state. So let's define the estimated state variable. Words are hard this morning. X hat. Got to get that apostrophe in there so that way you don't critique my English writing later. Yes. All right. So the dynamics that govern X hat are given by the following equation. It's given by X hat equals A X hat plus B U plus L Y minus C X hat. Okay, L is what I'm going to call the observer gain matrix. And it is in, so L belongs to the reals N by M, where N is the number of states and M is the number of measurements. That was ugly. All right. So C X hat equals to Y hat is my measurement. It's my measured output. Y hat is, so if I go back up into here, this is actually L Y minus Y hat. So the actual state versus the estimated state. And ideally we want those to go to 0, so that way I have a, and I forgot my dot on X hat dot. That way I actually have my system more or less consistent with what the actual states would be. So let's define the following. Define E of t, which is equal to the error. It's x of t minus x hat of t to be the error. It's the error between the actual and the estimated state. Then E dot of t is equal to x dot of t minus x hat dot of t. And so what I'm going to do is I'm going to plug in these equations. So I know that E dot of t is equal to ax plus bu minus ax hat plus bu plus L times y minus cx hat. All of this is in parentheses, so the bu part is going to cancel out. Bu cancels out, so I've got the following. I've got E dot of t is equal to ax minus x hat minus L y minus c x hat. But I know that x minus x hat is just equal to the error, right? This is just E of t. So E dot of t is equal to A times E of t minus L times C times x minus x hat. If you don't see where that came from, y is just equal to cx, right? So what that means is that this is also E of t down here. And so I've got that E dot of t is A minus LC times E of t. So this is the dynamics of the estimation error. So there's a couple things that I should notice from this equation. And before I push on, I might point out that the only way that a system observer can be decided is if the system is observable. Now, the caveat there is that there are some situations in which I can design a partial observer, but let's say I want a full estimation of the states. That only works if the system is fully observable. Alright, so what are some things I should notice about this? The first thing I want to notice, which plants the seed for a future lecture, is that the estimation error does not depend on the input or control. It does not depend on U, which is the input or control. The reason that that's great is that it may mean that the dynamics of the controller do not impact the dynamics of the observer. The solution of this equation, this differential equation, is that E of t is equal to E to the power A minus LC t. That's the matrix exponential of A minus LC times E of 0, the initial condition of error. And the performance of the observer, the performance of the observer is, oh my goodness gracious, my ability to write and speak is just a struggle in this video. I'm sorry. I'm hoping that you're still following along. The performance of the observer is governed by the roots of the determinant of SI minus A minus LC equal to 0. Alright, so what I mean here is that the dynamics of the observer are governed by the roots of this equation. Specifically, the roots, if I call S my variable, A and LC are matrices, I is the identity matrix of size n by n. So let's do an example of doing observer design. So let's consider the following. Let's consider x dot equals ax plus bu, and y equals cx, where a is just going to be 0, 1, 16, 0, and b is equal to 0, 1, and c is equal to 1, 0. And what I want to do is I want to find observer gains so that way the estimation error has a zeta, dead worm, of 0.8 and an omega n of 2 radians per second. So that's what I'm looking to do. Okay, so the first thing I need to do is I need to check observability. Check the observability. So my observability matrix is equal to CA. So first quote-unquote row is C, second row is C times A. So C is 1, 0. And then if I take C times A, I've got the first, so C is 1 by n, then I've got n by n. I should get a 1 by n back. And what I get is I get 0, 1. All right, so the row times the first column, so 1 times 0 plus 0 times 16. I'm gesturing with my Apple Pencil as if you can see that on the screen. And then I've got 1 times 1 plus 0 times 0, and so that's what I've got. So I know right away that there are exactly 2 linearly independent rows and columns in here. So the rank of O is equal to 2. Of course, you could do that in MATLAB or Python, I suppose, if you use the control systems toolbox that you can download for Python. You can find the rank by using the command rank. So since this is true, if the rank is equal to the number of states, then the system is observable. If it wasn't, this would be a real short example. So, next thing I need to do is find the roots of the determinant of Si minus A minus LC in parentheses equals to 0. So, obviously I'm going to need to do some matrix math here, so I'll take A minus LC, which is equal to my 0, 1, 16, 0 minus L1, L2 multiplied by 1, 0. And that's equal to 0, 1, 16, 0 A minus, and then I've got L1, 0, L2, 0. So when I combine that together, I've got an answer here, which is equal to negative L1, 1, 16 minus L2, 0, or Z. So now I want to take the determinant of Si minus A minus LC and set that equal to 0. So that's the determinant of S times the identity matrix of size n by n minus the matrix I just found, negative L1, 1, 16 minus L2, Z, and set that equal to 0. So that's going to be the determinant of, I'm going to just go ahead and combine these. I've got S minus minus L1, so S plus L1. I've got 0 minus 1, so negative 1. I've got 0 minus 16 minus L2, so that should be L2 minus 16. And then I've got s minus 0, so just s. I want to set that equal to 0. So to take this determinant, I will take the on diagonal multiplied minus the product of the off diagonal. So let's do that. I've got s plus L1 multiplied by s minus -1 times L2 minus 16. So the minus 1 cancels, and so I've got s squared plus L1s plus L2 minus 16 equals to 0. And then what I want to do is I want to compare this to my standard characteristic equation for a second order system. So let's compare this to s squared plus 2 zeta omega n s plus omega n squared equals to 0. And I know, because I told you what I want zeta to be, that this is going to be s squared plus 2 times 0.8 times 2 times s plus 2 squared. So in other words, this is equal to s squared plus 3.2s plus 4. And then I'm comparing that to s squared plus L1s plus L2 minus 16. Those two things are equal to each other. So I know that L1 must be 3.2 and L2 must be whatever 4 plus 16 is. Whatever that magic is, L2 is 20. All right, and so I've designed my first observer. In the next lecture, what I'm going to do is I'm going to put this together with the control design that we have seen earlier, and we're going to put that together to make a combined controller, and so we'll see that next time. All right, that's all. If you have any questions, please feel free to hop in the Discord chat or leave a comment below. As always, thanks for watching.